Alright, in 12.2 we are going to do the arithmetic series. Hopefully that kind of sounds familiar because we did arithmetic sequences in secondary 1. Now, sequences was talking about finding the pattern. Series is about actually finding the sum of all the terms. Okay, so let's go through over some stuff because I mentioned this already. A sequence is a list of terms in a specific order. Okay, a sequence can be finite, so it has a beginning or an end. Finite also means that you can count it. I'll be able to count it. Where infinite has a beginning, but it continues forever. Okay, so if something continues forever, you can't count it. If the pattern in the sequence has a common difference, we call it an arithmetic. Just like the linear functions we saw in secondary 1, hence me saying secondary 1. And then if the patterns have a common ratio, that was geometric. So we are going to focus on arithmetic today, okay? So a series is the sum of all the terms. Series can be finite or infinite. An arithmetic series adds the terms of an arithmetic sequence, and a geometric series adds the terms of a geometric sequence. So what I want you guys to get used to is that this Greek letter, sigma, we can say is a summation. So it's the summation of all the terms from one point to the other. So let's look at how the summations are set up. Okay, now this is not always the formula. This is the explicit formula for the sequence itself. So this could be any different formula. This example just has it being 2k plus 1. Okay, so what we're going to do is look, when we do the function itself, usually it's an x, a sequence is n, remember a subset n, and a series is k. So we're going to try to just use k throughout this whole thing just to get the right term. So the bottom here tells you where k begins. So remember, just because we have a certain sequence doesn't mean we're just finding the series, the addition of all the terms from term 1. We can start at term 3 if we want. And then the number that's going to be on top of the sigma is our last term. It's not the value of our last term, but what term we're ending at. Okay, so we're going to do this the long way, and then we're going to find some ways to be able to shorten it up. Okay, I don't want you really using your calculator right now. I want you to do it the long way. Okay, maybe for D you can use your calculator, but do not find the summation button on your calculator. I want you to see this out straight. Okay, let me make this where it's reasonable. Alright, so this is telling me I'm going to start with the third term and go all the way to the seventh term. So what I mean by that is I'm going to plug in 3 for k, but this is cubed, so I'm going to start with 3, and then my next term, of course, is going to be 4, 5, 6, and 7. So I want to see this written out when I ask you to write out and evaluate. Now, of course, this is going to be a little complicated, so yes, at this point, you may use your calculator. Now, when you use your calculator, I'm going to try to do these calculations faster so I don't have much time on the problem, which, of course, is not helping us out when we are still having focusing issues. So we have equals, and you should get 775. Okay, in the next one, we're going to start with term being 1, or k being 1, and we're going to go all the way till the fifth term. So in other words, plugging in 5 for k. So I get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Right? When I do all of that in my calculator, I will get the value of 55. So the summation is 55. Okay, do the same here. We're going to start with 3 and end with 8. So I get 2 times 3 plus 2 times 4 plus 2 times 5 plus 2 times 6 plus 2 times 7 plus 2 times 8. And we're stopping at 8. Just keep in mind every time what you're going to stop at. And that, if we do that together, we get 66. Okay, and let's do the last one. As you can see, our equation here has 2 k's in it. So make sure you put your value of k in both spots. So I'm going to start with 1 because that's where my lower limit is. So I have 1 over 1 plus 1 plus 2 over 2 plus 1 plus 3 over 3 plus 1 plus 4 over 4 plus 1. Okay, when you do this in your calculator, make sure you're using parentheses around those fractions. And this comes out to be a decimal. So when you do that, change it into a fraction, which you go math, enter, enter. And we get 136, or 163, goodness, over 60. Okay? Now, that's your basic just setup of what it means to do that. Okay, so here we go. Now let's go backwards, because the last time we did this, we went from sigma notation, and we showed the pattern and the addition, the summation of our terms. So now we're actually going to look at the sequence, and we're going to make it in sigma notation. So the one thing I want you to keep in mind, though, is just glance at it and see if you can see an easy pattern, okay? So if we look at this, I'm like 1/3, 1/4, 1/5. What are we doing? Well, in the denominator, it looks like we're adding 1 each time, right, guys? And if you look, it looks like we're starting at 3 and we're going to 10. So if we do our sigma notation, and I know it's going to be hard to get used to, it's like that E there. Remember, our starting point is always at the bottom, so k equals 3. And we're going to, well, let's make sure about this. We're going to 10, right? So we got to be careful, because is 10 actually the last term here? Well, if we look, let's see, we go 1 over k, because we're starting at 3, so it's 1/3, so on and so on, right? But if you look at this, would this value be 10 or not? Yes, it would, right? Because our last value would be 10 in there. Now, is this the only one that we could set up? Technically, no. If we wanted, okay, so there could be another one here. If we wanted to start at k equals 1, what would our equation look like? Well, it would be 1 over, because 1 stays the same. So let's put k in there. K is 1, but we want the value to be 3. So we would say k plus 2. Think of our next term. If we plugged in 2, 2 plus 2 is 4. The third term, 3 plus 2 is 5, so on and so on. But the difference is now we are no longer looking at the 10th term. We are actually going to the 8th term, because 8 plus 2 is 10. So that's going to be up to you on how you want to analyze what's going on. Either answer is correct, but let's do the easiest one. And the easiest one is saying, hey, I start at 3. All right, so let's see how this might get a little bit difficult. So we have 11, 17, 23. Well, there's nothing really obvious here, but if you look at the pattern, what are we doing each time? We are adding 6. And if we're adding by the same amount here, this is actually our linear, our slope-intercept form. Okay, so when you know you're going to do a linear equation, first of all, you always want to start out with k equals 1, that first term there. Now, whatever you're adding by is the slope of our linear equation. Now, on our side work, so I'm going to divide this up here, I need to make sure that whatever when we plug in 1 to this first term, we need to get the value of 11. Okay, that is how we know what the y-intercept is going to be here. So, again, if I plug in 1, I know the value must be 11. So now I'm going to solve. So I get 6 plus b equals 11. So b equals 5. And I am able now to put the plus 5. So plugging in that first term, 1 and finding that first term allows us to find the equation. But now we need to figure out what that last term is. Remember, your last term, the value is 71, but we need to figure out what actual term that is. So what we now do is actually set our equation, which is 6k plus 5, equal to 71, because we know the value is 71. And now we're going to solve for k. So we get 6k equals, and then if we subtract 5, we get 66. So k, which is the term, is 11. And that is what we put on top. So this is now our answer. Okay, so make sure we're going to go through these steps again on how to get the sigma notation. Okay, so here again for C, not so much an obvious answer, but if you look at these numbers, what's going on each time? I'm subtracting by 2. So what I am going to do is start with k equal to 1, because our first term equals 50. Let me see if I can get that to focus. Okay, so remember that this change here is our slope of our linear equation. So far I have negative 2k. And with my side work, just like I did before, I'm going to say negative 2. Now, remember, what did I do before? I plugged in 1 for the first term. I'm going to see what we're going to add to that to get the value of that first term. The value of that first term is 50. So I get negative 2 plus b equals 50. So b equals 52. Okay, so we get plus 52. Now to add on to the to figure out what term we end at, remember the value is 30, but we need to remember what term number it is. So I set my equation, my formula here, to 30. And then I solve. So negative 2k equals negative 12, and k equals 6. And we are done. So again, because we are talking about sequences and series, you don't start at 0. Whenever you see a pattern, a sequence, it's always starting at term 1. So this is why we have k equals 1. All right, let's look at this next one. Do you see something that's easy to recognize? Well, if you don't, let's check on the change. Well, if you see here, the change is different each time. So we can't do linear. It is not y equals mx supposed to be. So let's go back to, hey, is there a pattern I see? Well, first of all, I see that 2 is always in the numerator. What do you see with that denominator? 4, 9, 16. These are all squares, right? Perfect squares. Let's put 2 over 1. 1 is a perfect square too. 1 squared, 2 squared, 3 squared, 4 squared, so on and so on. So actually we're taking our term squared. All right, so let's start making our summation. We're going to start at 1 in this case because 1 squared is 1. It looks like this is our equation. And now what would be our last term? Well, what term or what number do you square to get 81? Because we're squaring it. Well, that would be 9. And that is our final answer. All right. Next. So what we've been doing right there is we just went back and forth of going from summation notation to the sequence and actually adding them up by hand. And we went backwards. We saw the sequence or the expanded summation and we made a sigma notation. So the idea is, though, is there a faster way that we could find the summation without having to write everything out? And there is. Okay. Now the reason why we want a simpler way is because what if I asked you to do start with term 1 and add all the way up to term 100? The last thing you want to do is write 100 terms and add them together. There has to be an easier way. So we can do it by this. We're going to look at the finite of this. Okay, so we're going to be able to add up into a certain point. So these are the two formulas that work. The sum of our notation is n, which is the number of terms, over 2 times the first term plus the last term. Okay. Or there's another equation that works very well. It's the number of terms divided by 2 times 2 times the first term plus the number of terms minus 1 times the difference. So you want to make sure you know what these variables mean. Now, if we have two equations, one must be better than the other, correct? So let's check it out. Which one would be better for which situation? Well, okay. In this pattern right here, we have term number 1. We have the n term. The only thing we're missing is the number of terms, right? So either way, we still need the number of terms. But since I have the first term and the last term already, I'm actually just going to use this first one where the sum is n over 2 times a subset 1 plus a subset n. Now you could use the other one, guys, and you can do the difference and everything. That's up to you. We should come up with the same answer anyways. But what I like about this is if I plug in right now, I see that I am only missing the n value. So this is -5 plus -71. Now, how do I find that n? How many terms did I use? Well, we can look at the pattern and then do it with our fingers, or we can do it algebraically like we did with the summation. So what is happening every time here? Well, we are subtracting 6. So if you think about it, arithmetic, that change, right, is these slopes. So I have -6, and then I have k, right? Well, in this case, let's do this because we want to find the whole equation, right? So let's do -6 times 1 plus b equals -5, just like what we did on the other page. So I get -6 plus what equals -5. So we get b equals 1. All right, now we can use that, right? We have -6k plus 1, and we need to figure out what k value, what term is -71 value. Okay, so now we're going to solve that through. -6k equals -72, so k equals 12. K is 12, so we're going from 1 to 12, so we're dealing with 12 terms. So now I can look at this as the sum is 12 over 2 times -5 plus -71. And now if I do that in my calculator, because it's going to be easier, that means the sum of this sequence is going to be, or this series is going to be -456. Now I want to point out something that's been going on throughout these whole problems. Has k ever been negative? No, it's not, because we're counting the term, not the value. The value has been negative, but the term itself. We always start with 1 and we go up. So there's the first term, the second term, the third term, the fourth term, fifth term, so on and so on. But you would never say the -1th term. Okay, so k will always be positive. So if you run into some algebra and your k is negative, you've done something wrong. All right, let's look at B, because this is starting with our summation. So if you look at this, what does this give us? This gives us the first term. It gives us the last term, or the last number of term, not the value of it. It also gives us the difference. Okay, so there's a couple things we could do here. And for fun, I'm going to use the second equation there so you can see how it's used. But again, you don't have to. So if I did sum equals n over 2. Well, we know n in this case, right? We know we have 8 terms. Okay. We know that it's going to be 2 times the first term. Well, how do we know what the first term is? Well, we don't know that yet. And then we say plus, and we have 8, again, because 8 is the number of terms, minus 1, times the difference, which in this case, the difference is 4. Remember, the distance is always what's in front, or your slope, what's in front of that k, okay? So we need to figure out, how do we find the first term, or the value, I mean, of that first term? Well, all we have to do is plug in 1 for k. And what do you know? We get the value of 7. Okay, so what I'm going to plug into my calculator is S subset n. We don't plug that in. We plug in the 8 divided by 2 times 2 times 7 plus 8 minus 1 times the difference of 4. And when we do that out, we get the summation of 168. Now, if you wanted to use the other equation, of course you need the first term and the last term, so you would have to plug in 1 for k to find that first term, and to find the last term, you would plug in an 8 to find that last term. Either way, we should still come out with 168. All right, one more, and we're gonna put this into a story problem situation. And by the way, this is what businesses do all the time, especially when you're trying to make a presentation to make money or anything like that. You want to predict and look at the max and everything like that. So let's look at this one. It says a theater has 15 seats in the first row. So what does that mean? The first row is a subset n. That means the value of it is 15. And it increases by 3 each row. So really, what is that saying to us? Well, all right, so we start with 15, and we go to 18, 21, so on, right? So that's what our pattern looks like. Now we are going up to a subset 30. Okay, we are looking at that last term there being the 30th term, but we don't know what it is. So right now what it wants us to do is make an arithmetic series to represent this. So I'm actually going to write it in sigma notation. So there's my sigma. We're going to start at k equals 1, and we're going to k equals 30. Now, how do we make our equation? Well, remember, our change is our slope, and it's going up by 3, so we have 3k. All right, well, we need to know what we start with. When we plug in 1, what makes it equal 15? So think of it as 3 times 1 plus what is 15? Well, that's 3 plus b equals 15. So b equals 12. So there is our sigma notation. Now what we're going to do is see what is the actual sum of it. What's going to happen with our theater if we filled up? How many seats are there? Now that would be kind of a pain in the butt to write out the 15 seats and 18, then 21, then 24, so on and so on, all the way to the 30th term because there's 30 rows, right? It's easier to do one of our equations. Well, again, either one is totally fine, but since I know the difference is going by 3, we start with 15. All I would have to do is figure out what, and we know that there are 30 terms. We don't even need our last term. So I'm going to use the summation equals n over 2 times the 2a subset 1 plus n minus 1 times d equation. I'm going to write that down so you see which one I'm using. So let me plug those values in. So s subset n equals the number of terms we have is 30. A subset 1 is we're starting out with 15 seats plus 30 is our number of terms minus 1 times, well, our difference is we're positive 3 because we're going up by 3. When you do that in the calculator, we end up getting 1,755. Now, of course, this is a situation, so I want you to use your units, which is seats. All right, so what's the final question? What does this help us with? I know there's 1,755 seats in the theater. What's great is you can now say, well, if we charged $7.75, what will we be making, or what money would be brought in if the whole theater was filled? Let's say on the day of, like, when Harry Potter first came out, or Lord of the Rings, or Infinity Wars, right? All of that theater was packed, so we could see ahead of time how much money we were getting in. So now with this one, all we have to do is take our total amount of seats and multiply it by 975, and we know to fill this theater that they would be bringing in $17,111.25. And don't forget, we need our units, so we put our $sign out front. All right, there we go.